about machine learning, and throughout the presentation we're going to talk about the definition, kind of its history and how it's connected to some other fields. We're going to look at some examples of supervised and unsupervised learning. Benjamin is going to talk about some important parts of machine learning algorithms and big data and some of its application. And then I'm going to give a short summary of the presentation. So machine learning is a very broad field. We're going to start off by defining it sort of. In 1959, Arthur Samuels tried to define machine learning as the field of study that gives computers the ability to learn without being explicitly programmed. Arthur, he wanted a computer program to be able to play checkers. So what he did, he programmed it to play thousands of games against itself, and eventually the program could beat even Arthur. Later on, in 1998, Tom Mitchell gave a slightly more formal definition of machine learning, which have been widely quoted, and it goes: a computer program is said to learn from experience E with respect to some class of task T, and performance measure P if its performance at task T, as measured by P, improves with experience E. So if you would apply this to Arthur's checkers example, then the task T would be to play checkers. The experience E would be playing thousands of games against itself, and the performance measure P would be the probability to beat a new opponent at the next game. There is actually still no real formal definition of machine learning. Machine learning practitioners haven't really agreed upon, but to summarize it, you could say that it's a method of data analysis that automates analytical model building. Using algorithms that iteratively learn from data, machine learning allows computers to find hidden insights without being programmed where to look. So now we're going to look at more the history and its connection to other subjects. Machine learning has borrowed a lot of models and methods from many fields, but it was mainly developed from artificial intelligence. Early on, artificial intelligence researchers, they wanted machines that could learn from data. And the approach to this problem led to the beginning and start of neural networks, which have played a huge role in machine learning. But data analysis and statistics, also neural networks, came out of fashion like the 1560s or something, and expert systems based on if-then rules was really dominating until the 90s, when computer power got stronger, and then machine learning got recognized as a separate subfield to artificial intelligence and really got popular. And then it also changed its goal from achieving artificial intelligence into tackling more solvable problems of practical nature. It also shifted focus away from the symbolic approach it had inherited from artificial intelligence, and went more for methods and models borrowed from statistics and probability theory. So yeah, now it's pretty much considered a subfield of computer science and artificial intelligence, but it's also very, very strongly connected to both statistics and probability theory, and it's connected to a lot of fields also, such as neuroscience, information theory, and signal processing. All right, so we're going to look at two main machine learning algorithms, which are supervised learning and unsupervised learning. We're going to start with supervised learning. Supervised learning is the machine learning task of inferring a function from a labeled training data. A supervised learning algorithm analyzes the training data and produces an inferred function which can be used for mapping new data. And two very common examples of this are regression and classification. Regression is quite a basic statistical tool, which I believe you've all seen in statistical courses. And it analyzes and estimates the relationship between variables. So in these cases, the dots would represent the training data, and the curve, the defeated curve, would sort of represent the inferred function, which can be used for, if you give it some new in data, it will give the output. And there's both linear regression and non-linear regression. And then there's classification. Classification is the problem of identifying to which of a set of categories a new observation belongs on the basis of a training set of data containing observations whose category membership is already known. And in this case, the training data would say the crosses and dots, and the algorithm would make this line or separate them. So when given new in data, the algorithm could say which group the data belongs to, pretty much. I think you've all seen this in the neural networks course. And then there's supervised learning, which is the machine learning task of inferring a function to describe hidden structure from unlabeled data. So instead of giving it a training set, you just give it a lot of data, and the algorithm itself find the structure within. And a common example of this is clustering. So in the first example, the above picture, we can see that the algorithm has sorted out the data into 5 different groups, and each group will have more in common with each other than do the other groups. Yeah, in the second example you can see that, for example, the green, there are more connections between the green nodes than from the green nodes to the blue. And that's how the algorithm could say that the greens have more in common, and therefore is the wrong group, the wrong cluster. So yeah, these are the basics of supervised learning and unsupervised learning. Now, Benjamin is going to talk about more real examples of this, to build up algorithms.
Okay, so now we know what unsupervised and supervised learning is, and I mean what method you use there is dependent on the data you have. If you have labeled data, you can use supervised learning. If you don't, you're forced to use unsupervised learning. Another way to represent or to get a framework for talking about machine learning algorithms was proposed by Pedro Domingos in a recent paper in 2012, which has been cited a lot. And that division is representation, evaluation, and optimization. And representation is what function or how do you represent the function that does the actual labeling or whatever is your task of the data. So that would be the linear regression or the neural network, and in artificial neural network case. And then you have the part that's the evaluation. That's how you tell or how you tell how good your machine learning algorithm or how good the representation is at its task. And this could be classification error, it could be some kind of utility function. And then lastly you have the optimization, and this is the method you use to improve your representation, your function that determines the outputs. And really there are a lot of different ways to do this, and that's maybe why you can say that machine learning is such a broad field. And this is just a table showing like some of the different examples. And here you have naive Bayesian, which is going to be used a lot in the algorithms for machine learning course if you're taking it. And then of course neural networks is another way to represent a function that determines some output data. Evaluation is kind of, I don't know, it's kind of simple, and it's just a bunch of different ways to say that, to rate the performance of your representation. And lastly, optimization. I mean, you have the gradient descent, which is used broadly, in a lot of different ways, and then but you can also do it in a lot of different ways, like just searching all the possibilities of your representation. To exemplify, I just took the home assignment number 4 from artificial neural networks, and here you obviously have the representation of an artificial neural network that does the classification of these points on this graph. The evaluation is the classification error. I mean, you actually use, you take one data and use the classification error for that, and then you backpropagate it. And with the backpropagation, you get, you can do gradient descent on the individual weights, and that is the optimization. So combining these different 3 parts, you can get different machine learning algorithms. And I think it's a good way to think about different algorithms. So now to the biggest field of machine learning. This is obviously big data. I mean, big data is you could say it's the state right now that we have a lot of data mostly from the internet and other sources like that. We have accumulated a lot of data, and a very good way to analyze this data to get good output or good things is by machine learning. First, an example is labeled pictures, and I mean this could either be tagged pictures on Facebook, or it could be just a database of pictures and labels for what they are. For example, this picture with a dog and ball in the snow. And there's a certain database that's called ImageNet that has about up to 15 million examples of pictures, simple pictures of things with a label to them. And this database or this organization has a competition that is happening every year where you should have a machine learning algorithm that identifies what is on the picture, and the performance of this has been steady for like from 2010 to 2012. But in comes deep learning. Deep learning is a algorithm based on artificial neural networks, and some say it's only like a buzzword or a thing to make it popular again. But what it does differently is that it incorporates unsupervised learning within the learning algorithm, and this is to create what we call it, like the deepness of the deep learning is that you have the deepness of the deep learning is that you have example is that it recognizes features of an image. In this case, like it could recognize the eyes of the dog, which then feeds into the next layer of the neural network as with strong connections to maybe dog, human, and stuff like that have eyes. And the other example could be like it recognizes letters on a photo of a text, and with the next layer then there's a word I'm looking for, but so it recognizes features by unsupervised learning and then categorizes them with the help of the labeled data. That's not really. I think I lost myself in that thought, but I hope you understand what I'm trying to say. So then you can see that this deep learning thing has really become a big thing, and has really revolutionized this computer vision, which is recognize this thing on an image, basically. And then you have the face recognition of Facebook where machine learning has a big part in their algorithm that they use to recognize the faces, so you can easily tag your friends and stuff like that. Okay, so next thing where there's a lot of data is sound to text. I mean, you can imagine just all the audiobooks are basically a mapping from sound to text. And this can be used to learn to recognize speech and translate it into text. And phones widely use this as a part of their speech recognition, but I know in October last year, Apple bought a startup in deep learning to apply that method to the speech recognition. Then you have, of course, the obvious thing when you think about big data is the internet using patterns, and that's just every click you make on a social network, on a search engine, is registered and stored for your particular user, and that data is then used to categorize your user to give specific targeted ads to you. And this is my profile from Google. Apparently I'm 35 to 44 years old, I don't know why. Probably, I don't know, maybe the board games or something, I don't know. But usually it does a really good job of giving you targeted ads. I mean, you can recognize this if you just watched a video about something, you can get an ad about that just directly afterwards. And this is probably, I mean, this is the most lucrative field at least, and brings the most money. I mean, most of Google's income comes from this, from just giving the targeted ads and different services like that. And lastly, I want to talk about the human genome. And I mean, this has probably the most like good effects if we could properly analyze stuff like this. But the big trouble here is that there's a lot of missing data. I mean, when you look at the drug companies, they have their own research and they don't want to like release all the data that they have. And of course, like it's a question of privacy also if your medical records can be used for whatever reason or stuff like that. So there's a lot of missing data, but right now the British government is doing a project where they're trying to get 100,000 full genome sequences from people with very specific diseases and also different cancers and also their siblings and parents and children to get like a huge amount of data to be able to do the machine learning algorithms on that data to be able to say something about which gene causes which thing and stuff like that. So this is a bunch of different applications in big data, and that's really where the money is right now for machine learning in general, and that's why I think it's the most interesting part, because if you can make something attractive for the market, then you can really be able to do a lot of research in it. And that's, I think that's it for this presentation.
Yeah, so what we've gone through today is sort of the definition that there really is none, but machine learning is programs that learn and can predict from data. Looks at some of the history and how it's connected to other fields. Then it's a subfield to computer science and artificial intelligence, but it's also very influenced by statistics. And we'll look at examples of supervised learning, the regression and the classification problems. Then we looked at supervised learning and clustering, which is just an unsupervised version of the classification problem. And then Benjamin talked about important parts of machine learning algorithms such as representation, evaluation, and optimization. And then we also talked about big data and some of its applications. And yeah, that's what we have to say today. Thank you all for listening.
Thank you very much. So I don't have a whole lot to add. I think it was a very enlightening summary and discussion of machine learning. And the only thing I can come to think of is natural language. I mean, in the context of big data. That's a huge potential. It's not all that much talked about in the context of big data. I think not as much as the connection with natural language processing. Most of the information that's out there is tremendously unstructured in the shape of text. So that's something to reflect upon, maybe. But thanks a lot, and the feedback forms are up there. The opportunities for sitting down in groups are Linsen down there. I don't know how familiar you are with this building, but well, in here down in the cafeteria. If my calculations are correct here, we should meet again at 14:25. That's what I make out of it, and that seems reasonable. Yes.
Should we present our questions?
Definitely. It's a terrible thing with the holidays and everything. I managed to get to turn up at least. It's always something.
Hello everyone, thank you very much guys for the presentation, it was very good. So we have prepared some questions.
Yeah, it's here. It's
Okay,
here.
it's already, okay, so, alright. So we are the review group, I'm Konstantina, David and Denko. And the first question we have for you, and for us probably, is what do and don't we want machines to be taught from us, actually? And another question is, are there subjects that we shouldn't really, that we cannot physically teach machine? And
Yeah, and the third question might be a bit of a continuation of the first one, and it's what kind of negative impact can we have, negative effects when we teach applications to machines? And the fourth question would be that since we now have the capability of processing large amounts of data, what fields profits the most from this?
Yeah, and question 5. According to the presentation, a good way to divide a learning algorithm is representation, evaluation, optimization. What other divisions can you think of? That's it.
okay.